So with our first day of class, we went over a brief history of numbers to develop why we need complex numbers. And so for today's class, what I would like us to look at it is that the idea that if all numbers can be written as a complex number, then we should be able to do all of those arithmetic operations that we've learned since first grade. So we're first going to define a complex number we will call as z. And I would suggest you cross it. Z is x plus iy, where x and y are both real numbers. So if we're looking at just different notations, we'll say that the real component of z is just the x value, and the imaginary component of z is the y value. And they can be visualized on an Argan diagram. This is a French mathematician, just like we call it a Cartesian coordinate plane. If we are graphing complex numbers, it's on an Argan diagram. So instead of x and y, we use real axis and the imaginary axis. And so there's a two-dimension analysis that we can do with complex numbers. So with complex numbers, just like any numbers, we should be learning to add, subtract, multiply, divide, and graph, both algebraically and graphically. So that's what these notes are for, and then I'll have a couple problems for you. So let's start with the basics. If we are given two complex numbers, 3 plus 5i and negative 2 plus 3i, if I wanted to add them, what I'm saying is we have the real components, 3 plus negative 2. Those are my real components, plus my imaginary components. And so that would give me 3 plus negative 2 is negative 1. 5 plus 3 is 8i. Now what I like to do, let's just change that color really quickly, is I like to visualize what that looks like on the Argan diagram. So if I was plotting Z1, it's 1, 2, 3, 1, 2, 3, 4, 5. So I'll label it as Z1, 3 reals, 5 imaginaries, just like a point. Z2 is negative 2 and 3i. 1, 2, 3. Z2. So what we are doing here is we are going out from the origin. So if you guys have any experience, we are looking at these two as, some people will call them vectors. So those are my 2 points that I'm adding. And you guys already see 5, 6, 7, 8, that the sum of these two numbers is at negative 1, negative 8. So I'm going to, again, graph that. And the reason why we're tying these graphs to the algebra, we'll say that's Z1 plus Z2, is what we did is we first started at Z1. And then, let's see if I can slide this. If I have everything to scale, what I did was I went from Z1 and then I moved Z2 in that direction. And if everything was to scale, these would match up perfectly at the location that I need it to be. But all you guys know that addition, order shouldn't matter. And so if order doesn't matter, then it shouldn't depend on which place I started with. Let's undo that. And so what we're getting here is this forms a parallelogram. Parallelogram. And all of the same properties of parallelograms will also hold true. Oh, and I should also say, this gives me an idea of why I'm looking at this all wrong, is 3 plus negative 2 is positive 1. 5 plus 3 is 8i. Well, if I can see that, let's shrink that down just a little bit. then the subtraction problem would also be similar. So if I have my 3 plus 5i, 1, 2, 3, 1, 2, 3, 4, 5, that's z1, 1, and then z2 is negative 2 plus 3i. There's z2. Well, subtraction should be like the opposite of addition. And so order does matter. And so if I'm thinking about subtraction in terms of addition, that would be z1 plus a negative z2, which means a reflection or a rotation of 180 degrees. That's what we're doing here. Instead of going up and to the left, like we have up here, we went left and then up. What I want to do is do the opposite of both of those, which means I would go right 2, down 3. And so if I negate this z2, I'm now in the 4th quadrant. You can see why I crossed my z's. And what we're doing is we're starting at z1, and we're going at opposite z2 in the same direction. So I'm going to take that piece, and again, we're going to get a parallelogram. And so the sum that we found, the answer should be here. Algebraically, it's a lot easier to see that it's just 3 minus a negative 2, that's my real component, plus 5 minus 3 with an I in front, which gives me 5 plus 2i. 5 plus 2i is what we see with this opposite side of my parallelogram. So that's addition and subtraction of complex numbers, both graphically and algebraically. Next up, we're going to look at multiplication, conjugates, and then division. So now let's take a look at multiplying complex numbers. If we quickly look at multiplying two complex numbers, it's just like foiling. So we multiply 2 times 2, 4, 2 times I, which is 2i, 3i times 2 is 6i, and then 3i times I, which would be 3i squared. Now we do have to leverage the idea that we know that I squared is negative 1. So I'm going to change that to a negative sign, and we have 4 minus 3, and then 2 plus 6. So we have 1 plus 8i. And that would be the product of these, let's say z1 and z2. Now let's take a look at what is happening on our Argan diagram. So our first number is 2 reals, 3 imaginary. There's z1. And then 2 plus I is z2. And what we got as a result somehow turned into 1 plus 8i. 1, 3, 4, 5, 6, 7, 8. So the product of these two complex numbers is larger. So I'm going to write this. The product is larger in scale, and somehow it was rotated counterclockwise. And that should sound interesting to us. If we multiplied, we're not just increasing the scale of these things, we're not just stretching it and making it further, but also inherently with multiplication is that we're scaling it, literally making it bigger, and we are rotating it in some way. it gets two of these transformations at the same time. A few other ideas that we need. The next one is the idea of a conjugate. We've seen this a couple times this year, but if you're given some sort of complex number, let's say it's a plus bi, let's get a little bit of ways from the x's and the y's, and just say that we have a real component and an imaginary component. Well, the conjugate of those is the real part stays the same. So how we read this is as z bar, is we are looking at keeping the real part the same, and the imaginary part is the opposite number. So let's just take a look at this. First off, it says multiply, given z equals 3 minus 4i. Multiply z times z bar. So let's first write out what z bar is. The real part stays the same. The imaginary part is the opposite sign. Now, if I graph these in terms of my real and imaginary axis, 3 minus 4i, that is our z, and then our conjugate is 3, 1, 2, 3, 4, plus 4i. Now I want you to think, if we're doing this in a visual manner, what happens when I multiply these two? In a similar way, we should see that it should scale and rotate. So let's write this out. We have 3 minus 4i and 3 plus 4i. So again, when we FOIL this, we have 3 times 3. 3 times 4i is 12i, minus 12i, minus 16i squared. Well, I squared we said was -1. So we have 9 plus 16, which is 25. And 12i minus 12i is 0i. And just like we saw before, what happens when you multiply a number and its conjugate, in this case, a complex number times its conjugate? Well, we definitely saw the scale part, but these two rotations somehow cancel each other out, and we have no imaginary part left. Or when you multiply a complex number and its conjugate, you're only left with real components left over, which is kind of this mind-boggling thing if we can see it geometrically, is that this goes out to 25, and it's now on the real axis, which is, if you think back to the algebra that we did, this is y. Now, the last two components that we need is what happens when we have fractions with complex numbers, and what happens when we have division of complex numbers. Now, these last two ones I'm not going to graph for you. We'll see in a second. But in order to divide by a complex number, it's similar to when we have square roots in the denominator. And when we had square roots in the denominator, we said we can't divide by a square root. And so we rationalize by multiplying the top and bottom by the square root of 2. So this would be root 2 over 2, which means our denominator is now a real number. So in a similar way, we are going to not rationalize, but realize this fraction, which means we're going to multiply by the conjugate. And by doing that, our numerator becomes 3 minus 4i. And as we saw, this is the exact same problem that we had before. We would end up with 9 plus 16, or 25. And so oftentimes people will leave it like this, but let's be specific. What we did here to realize this fractional complex number is we have our real component, 3 over 25, minus 4 over 25i. And that is how you realize. And if you know how to realize, then division is just a similar process. So we will multiply the numerator and denominator by the conjugate. So multiply by the conjugate. So in my numerator, let's just brute force this. 1 times 5 is 5. 1 times 12i. 4i times 5 is 20i. 4 times 12 is 48i squared over 25 minus 144i squared. So I squared is -1. 5 minus 48 is -43 plus 32i all over plus 169. So this division problem, this improper fraction, turns into -43 over 169 plus 32 over 169i. So that takes care of addition, subtraction, multiplication, and division. If you guys could please try the problems that are posted, which look like these ones, we get our addition, our subtraction, our multiplication, and our division. Also note, we can now raise things to powers. So we should be able to apply all of what we know here. I will see you guys next class. Take care.